Okay, so now that we've learned how to design a finite state machine from a state diagram to a circuit diagram and from a circuit diagram back to a state diagram, how do we actually do this in VHDL? So to write a state machine, an FSM in VHDL, it's really helpful to have your state diagram drawn because everything that you're going to be writing in VHDL will correspond directly to your state diagram. So we're going to walk through this example where we're going to write the VHDL code that models the FSM shown on the right. So this FSM here. Use a dependent PSNS coding style in your model and consider the listed state variables as output. Okay, so here we have a finite state machine and we see that it has input X and an output Z2. And also, so this output is a mealy output, Z2, and a more output, Z1, and we have 4 states, and this shows us how we get from each state to the next. And there's also a reset signal, which will be treated as an asynchronous reset to bring us back to the state. So I've gone ahead and copied this picture over here so we can refer to it as we are looking at the code for this. Alright, so first off, after we have our state diagram, let's draw our black box model, our entity description. So here's my FSM. We gave it a name. We have the input reset, the input X, and the input clock. And then we have output Z1, Z2, and it's said to output the state variables as well. So we're going to output our Y's. And the Y's are these state variables that we've listed in the diagram over here to the right, the 00011011. Okay, so this is our entity. We're going to start with the entity description and then describe its architecture. So here comes the code. Entity my FSM4 is. We have X clock and reset as both inputs of type standard logic. We have Y as an output, which is a standard logic vector of 2 bits, 1 down to 0. And we have Z1 and Z2, which are both outputs of type standard logic. So there's our entity description that described the black box we just saw above. And now we need the architecture to go ahead and describe our state machine. Okay, so the architecture, before the begins you do any signal declarations or component declarations. Well, I'm going to introduce to you now a new keyword called type. You're allowed to define types in VHDL. So we're going to define a type called state type so we can easily refer to these states as ST0, ST1, ST2, and ST3. It'll just make the code a lot easier to look at and manage. So we've just defined these states, a type called state type, and it could be one of these 4 types, or one of these 4 labels, I should say. Then we're going to create 2 signals that are going to have the type of this type that we've just defined. So you're used to declaring signals of type standard logic because standard logic is a VHDL defined type, but now you've described a type called state type, and PS and NS can be one of these state types. So PS and NS can take on ST0, ST1, ST2, and ST3. So guess what? PS and NS stand for present state and next state. Alright, so now that we've defined what we need to define, we're going to begin our architecture. And for every finite state machine, you're going to have a synchronous process and a combinatorial process. So the synchronous process is going to create those flip-flops for you, which are the state registers. And the combinatorial process is going to handle all of your next state decoder logic and output decoder logic. Okay, so let's start with the synchronous process. We declare a process and have our sensitivity list have the next state in it, the reset condition, and the clock. And we begin the process with the asynchronous reset, saying if reset equals 1, then the present state is going to become state 0, because you see in this diagram the reset will bring us to state 0. Else if rising edge of clock, then the present state gets the next state. So this is where we have the memory element coming in saying at every clock edge the present state is going to get whatever was defined as the next state. So now what is the next state? Well, we can use our combinatorial process to figure that out. So we've ended the synchronous process. Now we're going to begin our combinatorial process with our sensitivity list having our input x and our present state, because we need to know what the present state is and we need to know what x is in order to figure out what the next state and the output is supposed to be. Okay, so we're going to begin. We begin by initializing the outputs. So we're going to initialize the outputs to 0. So Z1 and Z2 are both 0. Then we're going to go ahead and look at what state we're currently in. So we're going to start by looking in having us be in state 0, which is this 0, 0 state. So case PS is, so when the present state is state 0, the output Z1, which is our more output, is a 1 in state 0. So we're going to get Z1 gets a 1. Then to determine what our next state is, it depends on what x is. So if x is 0, that's this transition here, x is 0. If x is 0, then the next state is going to be state 1. So we have x is 0, next state is state 1. And in that transition, we also know that Z2 is 0. So we go ahead and write that right there. So this line that I'm scrolling over at the moment is corresponding to this transition in the diagram. Okay, so else, that means else x must be 1. So if x is 1, we're going to be looking at this transition, this loop on state 0. So the next state is going to get state 0, and Z2 is going to get 1. So Z2 gets 1. And if, and then we've taken care of handling everything going on in state 0. Now we can see, what if the present state was in state 1? What are we going to do? So in state 1, when state 1, Z1, our more output, is going to be a 1. Then let's take a look at the x equals 0 condition, this transition right here. We're going to transition to state 2 and have a Z2 output of 0. So we're going to transition to state 2 and have a Z2 output of 0. Else, x is a 1. We're going to stay in state 1 and have a Z2 output of a 1. There it is. And if. So you do this for every single state. You can follow along later if you'd like for state 2. You look at state 2, you see what your Z1 is, it's a 0, you write that out, and then you look at your transitions and they correspond to these. Then you do state 3 and do the same thing, you write your Z1 and your transitions. And then when others, you just add that, even though there's only 4 states possible, just throw it in there just in case. Just assign it, since your reset state is 0, just assign your next state to state 0. And you can assign your Z1 and Z2 output to whatever you'd like them to be as a just in case. So yeah, because you're going to make your next state state 0, might as well assign Z1 to what's in state 0 and Z2 to 0 just because you feel like it. So I don't know if this is really that necessary because you've covered all of these, but it's always good to have a when others in a case statement. Alright, so we have finally modeled this whole state machine, and because we wanted to also output the state variables, we're going to add another statement here using the PS signal. So with the present state, select 0, 0 when you're in state 0. So it's now assigning the number 0, 0 to state 0, 0. Or make y 0, 1 when you're in state 1, or 1, 0 when state 2, and 1, 1 when state 3, and then having again a catch-all to have 0, 0 when others. So this is allowing us to output the state variables y. And there you have it. That is a VHDL model that describes a finite state machine. And how I go about coding these is I always have a model, or rather a template, such as this code right here in the textbook. I have that open. I have my state diagram drawn, and then I just go ahead and follow this template and follow my diagram and fill in what I need. So it's actually very simple. It's very methodical. You just go state by state following this template with whatever you have drawn in your diagram. Alright,